Hello, everyone. This is Tianxi. My topic today is differentially private binary and matrix value data query and XOR mechanism. I will follow this outline to present our work. First is about the motivation. Existing differential privacy mechanism usually consider the continuous and scalar valued query result. However, binary and matrix value query are also ubiquitous in many of the real-world applications. For example, we can model the structure of social network using binary adjacent matrix and represent medical record of people using binary samples. We also have binary data in traditional image processing due to data compression and quantization. So the target of this paper is to achieve differential privacy when releasing binary and matrix value queries to third parties. Here is the background on differential privacy. In the paper, we adopt the pure epsilon differential privacy definition and consider the query is the binary matrix that has n rows and p columns. The sensitivity of the query is defined like this, which essentially counts the number of different entries between FD and FD prime. The noise distribution we consider in this paper is called the matrix valued Bernoulli distribution with quadratic exponential dependency structure. Its PDF is shown in the first equation, and C is the normalization constant. This PDF may look scary, but essentially it only has three different parameters. First is theta, then lambda, and phi. And this is their mathematical definition, but I will not read through them due to the time limit. Instead, I will explain their physical meaning using the graphical examples. Theta I PQ is the correlation between two entries in the noise matrix, and these two entries is in the same row but two different columns. And the lambda is the correlation between two entries that are in the same column but two different rows. Finally, phi is the correlation between two entries belonging to different rows and columns. Here is the definition of the proposed mechanism. Specifically, giving a binary query result, we perturb it by conducting the exclusive OR operation using a binary random noise. And this noise is attributed to the previously mentioned probability distribution. In the paper, we show that the proposed mechanism can achieve epsilon differential privacy as long as this condition holds. It essentially means that the summation of the L2 norm of the eigenvalues times the query sensitivity is lower than the privacy budget. We also have the utility guarantee of the proposed mechanism. First, we define the square query error rate like this, which is essentially the ratio between the square norm of the error and the square norm of the query result. We can show that the expected query error rate can be computed like this, where the parameter pi can also be obtained from the parametric matrices of the considered probability distribution. Now we talk about how we implement this mechanism. First is to determine the parameters in the distribution. Recall that the privacy condition only impose constraints on the eigenvalues of the parametric matrices. As a result, there can be infinite number of such matrices in the design space of the noise. So to solve this problem and generate the parameters, we consider this optimization problem, which minimize the expected query error rate, but satisfying the epsilon differential privacy condition. And to solve this problem, we first notice that the expected query error rate is proportional to G pi, which is the ratio of two summations. Since the minimization of this expression is an NP-hard problem, we consider minimize its upper bound, which is characterized using the eigenvalues of the parametric matrices. As a result, the previous problem can be relaxed to this new one. Now the optimization problem is the upper bound of G pi. Please refer to our paper on how we solve this problem. Given the distribution parameters, the next step is to generate the noise samples. Recall that this is the scary PDF we are going to draw samples from. Since it is computational prohibitive to calculate the normalization constant, and as far as we know, there is also no available toolbox to generate the samples from this distribution. So to solve this problem, we resort to an existing work that proposes an exact Hamiltonian Monte Carlo approach to generate samples from a binary distribution. And we adapt their method to draw samples from the desired matrix value Bernoulli distribution. Here is the sampling procedure, and it is a variation of the EHMC procedure. So please also refer to the paper for the detail. In the paper, we consider different case studies, but in the presentation, I will only focus on the application on graphs. So the target of this case study is to query the structure of undirected graph under differential privacy guarantee. And the structure is characterized by the binary adjacency matrix. And the algorithm 3 gives the procedure to query the adjacency matrix with epsilon differential privacy guarantee using the proposed mechanism. First up, after generating the desired noise sample, we can get an intermediate result, but it may not be a valid adjacency matrix. So we need to first further post-process it to get A tilde to make the result be symmetric and have 0 diagonal entries. And clearly this is differentially private because algorithm 3 is owning a simple post-processing of the proposed mechanism. In the case study, we consider differentially private network statistics and degree distribution and community detection. We also consider two network dataset and compare the proposed mechanism with works that are designed to share graph structure under differential privacy guarantee, and also the works that are developed specifically for degree distribution estimation and community detection. I would like to highlight that all this work inject continuous value noise to some intermediate step of their algorithm. So different from them, our algorithm directly address the binary nature of the queried data. Here is the network statistics calculated by different mechanisms, and the subscription is the epsilon privacy budget. We can see in most of the cases, we can achieve network statistics that are most close to the non-private ones. And also for the degree distribution and the community detection, our mechanism can achieve lower KR divergence between the original non-private degree distribution and the differentially private one for most of the privacy budget. And similarly, our mechanism can also achieve higher average F1 score in terms of differentially private community detection. Thank you.